specific sample linear program. And in this video, we're just going to generalize that and to run the iteration on the general format of this linear program of this type that we've always been talking about. So we're just formalizing that. So our linear program, as we know, it can always be written like this: max C transpose X, such that these matrix equality constraints hold and the variable non-negativity constraints hold. And then we're assuming this is in canonical form for some basis B, where B is the particular set of indices corresponding to column vectors of the matrix A, and those particular columns are a basis for the column space of A. And then for this basis B, X bar is going to be the basic feasible solution associated to that basis. So we always have a basic solution. It doesn't necessarily need to be the case that it's also feasible, but in order for this to work, we need to start with a basic feasible solution. So again, there's another question about how you generate this in the first place. That will be for a separate video. Here our starting assumption is that we have a basic feasible solution for this basis. So yeah, and what does that mean? We're in canonical form for this basis B, so that means that the submatrix of A indexed by the basic columns is the identity matrix, and the basic components of C are all zeros. And then because X bar is the associated basic feasible solution for that basis, then all the non-basic entries of that vector are all zeros. And when you plug X bar into the objective function, what you find then is C transpose times X bar. Well, you just break it up into the basic and non-basic components. And for the basic components, the C's are going to be zeros, and for the non-basic components, the X's are going to be zeros. And that comes from just over here, what we just said. And so, anyways, you have a bunch of zeros times X's and C's times zeros, and it's just a bunch of zeros times stuff, and you just add zeros, and you get 0 at the end. So C transpose times X bar is 0. And then the idea is that one of these you're going to look for. So down here you search for a particular CK which is positive. So for some index K, hopefully you'll find a CK that's positive. And it's not going to be amongst the basic indices, because we already know the basic indices, the C's are zeros. So it's going to be some non-basic index where we have a positive C. And then for the associated variable xk, this particular index k, we're going to boost that variable. That's what I'll call the booster variable. And we're going to try to make it as large as we can, because that'll increase the objective value, because we'll have ck, which is positive, times xk, which is getting larger, and so that's going to make the objective function bigger. And so, yeah, so you're going to boost, so the xk will live in one of these non-basic variables here, and you're going to boost that, and that's going to increase everything, and then you're going to have to compensate somehow so that with the basic variables, so that you maintain all the feasibility constraints. But the idea is that because you have 0 coefficients in front of all the basic variables, it's not going to affect the objective value. So by boosting here, you're getting help. You're increasing the objective function, but it doesn't cost you anything. You get to do that for free, since the zero coefficients appear in front of the basic variables, so that'll never hurt you. So you get help and no harm from this boosting process. So let me just give you the outline real quick, and this is also just a very quick recap of how it worked in the specific case of that example from the previous videos. You start with this CK that's positive, so you have to find that, and then take the associated booster variable xk, and you call that t, and you just call it t just to indicate that it's the special variable that we're concerned with. And now you construct a new solution, we'll call it x prime, and the way that you construct that new solution is that first you define it for the non-basic components. For the non-basic components, all the non-basic components except for this k index, they're all going to be zeros. And that's just as the x bar is as well. There are zeros for all the non-basic components. Here it's for all the non-basic components except for the k index. And for the k index, you take it to be t. And again, that's just an aesthetic change, x prime. We can just call it x prime sub k, but we just call it t. Again, we're just calling it t to indicate that it's special. But anyways, that's what you do for all the non-basic indices. And for the basic indices, you have to figure those out afterwards. How exactly? Well, you use the feasibility constraints to determine it. In particular, you parameterize xb prime in terms of t, and you do that by using the ax equals b constraint. So we know that x prime is going to have to be feasible at the end of the day, so we need ax prime equals b. And if you just work out what that is, a times x prime, it's a linear combination of the columns of a. But for the non-basic columns, all the coefficients are zeros. That's what we just said above. X prime will have a bunch of zero coefficients for all the non-basic indices except for the kth index. And so for the kth column of A, that will have the associated xk, x prime k variable, which we're calling t. So we'll have t times ak plus the basic, a linear combination of the basic columns. And yeah, I mean, hopefully it's clear that a sub k is referring to the kth column of the matrix A. And this is constrained to be the vector b, and then you just, now that we also know we're in canonical form, so this A sub b matrix just disappears. It's just the identity matrix. And now you have this equation, and you can just move xb prime to one side and solve for it. So it's b minus tak, and this t variable is the only thing we don't know. The b and the ak data is already given, so that's what it means to have parameterized xb prime in terms of t. So we don't know xb prime, but it's in terms of t. And so once we figure out t, then we figure out all of xb prime. So how do we figure out t? Well, you use the other constraint, the non-negativity constraint. So we know that all the non-basic components are automatically non-negative, but for the basic components, we need to ensure that as well. And anyways, using that will give you what t is. And that'll give you this overall better solution x prime. It's better because we're boosting t, and it'll give us a value that's greater than or equal to 0. In this process, you also end up getting a new basis called b prime, and it turns out that this x prime that you generate is the basic feasible solution for this basis b prime. And so what that means is, so that's basically what these steps are. It's just verifying that it truly is the basic feasible solution for this basis b prime. And so you arrive at this blue comment here. And so what that means is that now we have a basic feasible solution for a given basis, and that's exactly where we started. So just put the linear program in canonical form for that basis, that new basis b prime, and now we're right back to square one. What do we have? We have a basis b prime. The linear program is in canonical form for that basis, and we have the associated basic feasible solution x prime. And now you just iterate this process over and over because, well, that's where we started, so we can do the process again, and that'll just give us successively better and better solutions. And in general, that's what simplex algorithm does. Okay, so now I'll go through the details of that. So we'll just slide back up and over here. So I think we're here. So yeah, just one more time. This is our form that we're working with, and here's x bar, a basic feasible solution for this basis b that we start with. And we're in canonical form for that. And so we first you just go through the list of C's and pick one where the C is positive. But you have to be careful about that because it could be there's a corner case, which is what if there are no non-basic components where C is positive? What if they're all less than or equal to 0 for all the non-basic components? And again, they're all exactly 0 for the basic components, so the only hope we had of finding a positive one was amongst the non-basic ones. Well, in that case, basically what you'll find is that x bar, your basic feasible solution, is already optimal. And the reason is that if you just take any feasible solution, x star, C transpose times x star, break it up into basic and non-basic parts. So the basic part goes away because the C coefficients are all zeros there, and so you're just left with Cn times xn star. And so that's this. And this is less than or equal to 0. And that's because we're assuming, in this corner case here, that Cn is less than or equal to 0. And by feasibility of xn star, it has to be non-negative. So I have a non-positive vector dot producted with a non-negative vector. And so, of course, then that's going to give me something that's less than or equal to 0. But on the other hand, so that's what OTOH is, on the other hand. C transpose X bar, we already showed was exactly 0. So we've just shown that for any feasible solution, 0 is an upper bound. You're never going to do better than 0. But on the other hand, X bar attains that upper bound of 0. And so that means that X bar is as good as it gets. So in other words, X bar is an optimal solution. And then you can terminate the algorithm. We're done in this case because, we've accomplished our goal. We've found an optimal solution. So that would be the end of the algorithm. But typically that won't be the case. But if it is, we've addressed the corner case. So now we can assume that there is, in fact, some ck that's positive for some non-basic index k. And so the associated booster variable will be xk. And so what you do is you define a new solution x prime. And as we've already said, so first define it for the non-basic components. And you do that so that all the non-basic components except for the k index are all zeros. And then for the k index, you just make this aesthetic change and call it, instead of calling it xk prime, you call it t. And then we'll figure out what t needs to be. But you do that afterwards, because next you parameterize the basic components of x prime in terms of t. And I already went through this on the outline, but yeah, so you just use the matrix equality constraints ax prime equals b, and that gives you this equation, and you can solve for xp prime, and there you go. You have a parameterization of x prime for the basic indices. Basic components, I should say. Okay, and so now you're going to use the fact that it also has to be non-negative to determine what t is. And once you know t, then you know xp prime, and you actually know all of the vector x prime. So how do we in particular, how do we get t here? Well, xp prime, it has to be non-negative, and so that means that we just parameterized xp prime here. It's little b minus tak, and that has to be greater than or equal to 0. And so you just rearrange, and you get b has to be greater than or equal to tak. But these are both vectors. So what does it mean for one vector to be greater than or equal to another? Well, that means that each of the individual components of the vector on the left-hand side has to be greater than or equal to the individual components on the right-hand side for the corresponding components, of course. And so here's a little picture just to help visualize that. So AK is the kth column of A. So, if I look at the matrix A, it just consists of a bunch of columns, A1, A2, here's AK, keep going, all the way to the last column, AN. By convention, you just assume that, you have notation. Notation is that there's M rows and N columns. And so the column vector AK consists of M components here, because there's one component for every row for a column vector. And so the components are A1k, A2k, on and on, all the way to AMK. And so, AIK in general is just the ith component of the column vector AK. It's also the IK entry of the matrix A, of course. Same thing. So anyways, we need this BI to be greater than or equal to TAIK for all row indices I. So I is iterating down the rows here. For every row, there's an index I. And you need that to be true for all row indices I, equals 1 to m. But we already know the BI is greater than or equal to 0 for all I. So in other words, the left-hand side is non-negative. And that's because, if you think about what it means to have a basic feasible solution, x bar is a basic feasible solution. So that means the non-basic components are all zeros. But for the basic components are exactly the entries of this vector little b here. That's what it means to be a basic feasible solution when you're in canonical form for that basis. And so since that vector x bar has to be non-negative because it's feasible, then that must mean, since it in part consists of the components of the vector little b, then all those components of little b must also be non-negative. And so that's how you get that this left-hand side here is greater than or equal to 0. Now, if this right-hand side, if AIK is positive, it might not be, but if it is, then the only way for this constraint to be true, BI to be greater than or equal to TAIK, That's if and only if t is less than or equal to this ratio bi over aik. You can't, what that means is t is this variable, it's xk prime here, it's what we're trying to boost as much as we can, it's our booster variable, but we can't boost it arbitrarily large. What we have here is an upper bound on t. It might have to be even less than this, but at best it's not going to be any greater than bi over aik, because otherwise you're going to ruin this condition, and this condition is equivalent to having the basic components of x prime being non-negative. Okay, so that's if aik is positive. On the other hand, if aik is less than or equal to 0, then actually, then you know that t is greater than or equal to 0. If aik is less than or equal to 0, this right-hand side is less than or equal to 0, and like we just said, bi is greater than or equal to 0. So then this automatically holds. bi is greater than or equal to t aik, no matter what t is. So this is independent of t. And so there's no constraint that's imposed on t if for a particular row index I, we have aik is less than or equal to 0. So what you do is, you just look amongst all the aiks that are positive. So for the various row indices I, you look down those rows and look at the corresponding entries in the column vector ak, and for the ones that are positive, like we just said, we need t to be less than or equal to bi over aik for those indices I, where aik is positive. But it has to be for all such indices I. So it has to satisfy all of those constraints. If it breaks even one of them, we've ruined feasibility. But on the other hand, we want t to be as large as possible. So what do you do then if you have a bunch of upper bounds and you need t to be less than or equal to all of those upper bounds? Well, you just look at the minimum of those upper bounds, and then you say, okay, take t to be that large, because we want t to be as big as we can, so take t to be the minimum of those. If it's any larger, it's going to violate the harshest of, the most restrictive of those constraints. But if it's any less, then we could just keep going until we get to this minimum upper bound here. And so anyways, that's what you do. You take t to be the minimum of these ratios for the aiks that are positive. But you have to be careful because, the one assumption I am making here is that such an aik exists. So what if, there's a corner case here, what if aik is less than or equal to 0 for all row indices I equals 1 to m? So in other words, that column vector ak is less than or equal to 0. Well, like we just said above, we have that bi is greater than or equal to t aik, no matter what t is. There's no restrictions on t that's independent of the index I as well. So then we have 0 restrictions on t. And so we can take t to be as large as we want. So b minus t ak is greater than or equal to 0, no matter what t is in that case. And basically what we're saying, so x prime, the basic components of x prime b, I'm just filling in what b minus t ak is. It's xb prime. It's greater than or equal to 0, no matter what t is. And so if you look at the objective function, the point is you're not going to, up here with this line, is that you're not going to ruin non-negativity by increasing t. Typically, the idea is that you're going to increase t only so much before this vector is in danger of becoming negative. But in this case, it won't. So you're free to increase t as much as you want. And then in the objective function, the objective function is ck times t. Everything else is all zeros, right? Because either the x's are zeros or the c's are zeros, but except for this particular index, special index k. And ck is positive, and then the associated variable is t, and you just make t to be arbitrarily large, and that makes this objective function value arbitrarily large. So I'm just rewriting it here. I'm saying ck times little t here is c transpose times x prime. It's just more explicitly written as the objective function. And so this is going off to infinity as t grows arbitrarily large. And so that means you can make your objective function as large as you want. There's arbitrarily good solutions. So yeah, in this case we say that the linear program is so-called unbounded. And that means that there's no optimal solution because you actually can generate a class of solutions that are tend off to infinity, that the solutions just get better and better and better, and there's no end. So that's called unbounded, and that's what happens when this vector when we're in this corner case where AK is less than or equal to 0. And so in this case, the algorithm would terminate because we've concluded that there is no optimal solution, and we've found a class of solutions that tend off to infinity. Okay, so that's a corner case again. So assuming that's not the case, then we can assume, if it is the case, we've addressed it. But if it's not the case, now we can assume that we have a row index I from row 1 to row m here, such that the AIK entry is positive. So again, in the column vector AK, I'm looking at the ith entry, and that's positive. And so there exists an I for which that's true. And that means that this minimum of these ratios that we were talking about before, that it's well defined. And so therefore we're free to take t to be this value, which is what we wanted to do. And this is a minimum of a bunch of ratios, bi over aik. So, but there's a finite number of them. So just take this minimum will be attained at some particular index r. So at row index I equals r, this minimum is attained. And so in that case, we know that t is exactly equal to br over ark, the attainment of this minimum. And there could be multiple rows for which this is true. It doesn't matter. It's fine. Just take any of the rows for which it's true and call that row r. I mean, you can have a convention for how you pick it, but it doesn't matter how you pick it, just as long as, I mean, we know it exists. So just for any such r, this works. Okay, so what is the rth entry in this the basic components of x prime? What is the rth entry there? Well, xb prime is little b minus tak. It's the rth entry there, and so that's br minus t times ark. And then now we know what t is. It's br over ark. It's the attainment of that minimum ratio. And obviously, you can tell that the ark's cancel, and then br minus br is 0. And so that means that the rth entry in this vector x, in the subvector x prime, the basic components of x prime, that the rth component there is 0. If we would have taken t to be any larger than br over ark, then this would have become negative, this component here, and that would have violated non-negativity. But of course we didn't. That's why we made that choice of t being the minimum of those ratios, and here's the attainment of it. And this is the harshest restriction here. And anyway, so this is as good as you can do. So we get that this component becomes 0. But just remember that xb prime is a subvector of the overall vector x prime. So within the subvector xb prime, this is the rth component that we're talking about, xb prime sub r, the rth component. But in the overall vector, it's not the rth component, it's some other component. So here's a picture. So x prime consists of a bunch of components, x1 prime, blah, 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 all the way to xn prime. And only some of these components are the basic components. So let's say I've circled the basic components as the green ones, and you see in general how that works then. And what I'm doing is I'm counting r down amongst the basic components to get that entry xb prime sub r. So I'm counting, amongst the green circled components, 1, 2, 3, all the way down to the rth one, and that's giving me the xb prime sub r. But in the overall vector, that's just some component with index not r, but just some other index, because it's in the context of this overall vector. So what entry have I hit in the overall vector? If I count r down amongst the green circled ones and at some particular component, what component is that in this overall vector? So let's call it the lth component. So say x prime sub b sub r is the lth component of x prime overall. And so xl prime is the rth basic component of this vector, so it's 0. And so what you do is you take, by the way, I should just point out, this is just a property of x prime. We've at this point we know what x prime is completely because we figured out what t is. It's that br over ark, and And then the basic components were parameterized by t. So now we know the basic components and we know t, and we already knew the rest of the non-basic components, so that's the entire vector. So now we're just looking at a particular property that this lth component is 0. And then the way that this works, to get the new basis b prime, well, it's a lot like the old basis. It is the old basis, except that you add in index k and you take out index l. So index l, no, it was part of the basis before. That's by definition what L was. It was the rth basic component. So it was in the basis, and K was not in the basis. That's initially, K was always assumed to be not in the basis. So this is anyways, all we're doing is we're exchanging K and L. So L used to be in the basis, and K used to not be in the basis. Now we exchange those two indices, and then correspondingly, for the new non-basic indices n prime, again, you're just exchanging, but in the opposite direction. So now L is part of the non-basic indices, and K is not. So yeah, that's how you get the new basis b prime. But actually, I haven't actually shown you. You should your spidey senses should be going off and saying that we haven't actually shown that this is a basis. I've just been using the word basis. We know that b is a basis, but we don't know that b prime, upon doing this exchange here, is a basis as well. So these are two facts that I'm assuming for now, and then we're going to prove these in just a moment. But let's just assume that these two facts are true for a moment, that b prime is indeed a basis, and I mean it is. I'll show you why in a second. And then the other fact is that what we wanted to show is that x prime was a basic feasible solution for this basis b prime. And so what would need to be true for that? Well, we would need that x prime for these new non-basic components, so for the n prime components, they would all need to be zeros. That's what it means to be a basic feasible solution for a particular basis. And so that's what this is saying. So these two facts together would imply that x prime is the basic feasible solution for this basis b prime. So we know it's feasible already. That's how we constructed it. We constructed it to satisfy all the constraints. So it is feasible, and then it's now basic as well as a result of as a result of facts 1 and 2 being true. Okay. And then finally, now that we have a new basic feasible solution, x prime, it's better than the old basic feasible solution, x bar, because look, I mean, c transpose times x prime is equal to all the components vanish, because either the c's or the x's are zeros, except for t times ck, as we've said before, and that's non-negative. T is non-negative, ck is positive. So this is at least 0, and 0 is exactly what c transpose times x bar was. We already showed that above. I mean, for the same reason, really. It's just that because the kth component here was also 0, whereas in contrast here, it's t, when t could potentially be positive. So that's why we're doing better for x with x prime than x bar. So we have a better basic feasible solution, and that's all we wanted. So now just put your linear program in canonical form for this new basis b prime, which of course we can always do, and iterate that, because that's all we're trying to do. We're jumping from basic feasible solution to another basic feasible solution, and the new one is better than the old one. And you just keep doing this over and over and over again, generating successively better basic feasible solutions. And at some point, you're going to either find that you're going to be in one of those two corner cases that we addressed above. Either it'll be the case that at some point there's just, because every time you put your linear program in canonical form, it's going to change what the values of C are and what the matrix A is. And so you have to reevaluate and say, okay, now, are there any C's that are positive upon putting it in canonical form for this new basis? And you have to keep doing that for every iteration. And at some point, you're going to end up in one of those two corner cases where either there's no C's that are positive, in which case you can finally conclude that the current basic feasible solution you're at is optimal, or you'll find that your matrix column vector AK is less than or equal to 0, and that will allow you to conclude that your linear program is unbounded. But in either case, you've shown either optimality or the unboundedness of your linear program, and that's how this goes. So yeah, simplex algorithm. It starts with a basic feasible solution, and then it goes to better and better basic feasible solutions until there's no more better ones, or there's just infinitely many. They could arbitrarily good. So that's it. So if you want to pause your video and just kind of like, appreciate just how neat that algorithm is, and how cleanly that all works. It's kind of mysterious why it's so clean, but it is so clean, and just all goes really smoothly, and it's a really cool algorithm. But anyways, obviously I'm not going to pause here in the video, so you can do that on your own if you want, but let's just keep going here. So there's still two things to address here. Why is B prime actually a basis, and why is it that, so these two facts that we assumed, right, and why is it that x prime is 0 for these new non-basic components for n prime here? So fact 2 is a little easier to show, so we'll do that first. We can show that this is true without assuming anything about B prime being a basis or not. We know explicitly what the indices n prime are, so let's just verify that x prime is 0 for those. And again, this shouldn't be surprising actually, because n prime is almost n. It's n but with an exchange. It's n but we added index L and we took out index K, and so x prime sub n prime is just this, and we already know that for all the indices indexed by n, that x prime is zeros for all those. We already knew that, with the exception of the index k. But we're no longer considering index k. That's exactly why we're removing that index and doing that particular exchange. So that was the only index for which x prime might not have been 0, but no longer a consideration. Now there is a new index that we do have to address, which is index L, and in fact x prime sub L is 0. So yeah, so this is just what we already said. So for all components besides L, we already know that it's equal to 0, because x prime sub n is equal to 0. And then we also separately determined that x prime sub L was equal to 0 above. That was like the definition. Remember, x prime sub L was the rth basic component of x prime, and that was the one that went to 0 by our choice of the booster variable t. So yeah, so then that means that all these components genuinely are zeros. And so we've shown that fact 2 is true. Okay, so it's a little harder to show that B prime is a basis, although it's nothing overwhelming, but let's just go through it. So, why is B prime a basis? So first, again, just remember B prime is very similar to B, but with an exchange. So first, the submatrix of A indexed by B, not B prime, but B, is the identity matrix. And actually, I'm not so concerned with the matrix itself. I'm more concerned with the columns that this matrix consists of. So don't think of this as a matrix. Think of it as a collection of columns. And the only reason I'm writing with matrix notation is just because that's compact. But yeah, think of it as columns. So this is a collection of columns, your identity matrix columns, and those obviously form a basis of the column space of A, because it's the standard basis. This is the identity matrix. So the columns of the identity matrix form the standard basis in Rm, and so this B is a basis. I hate these pop-up ads. Sorry about that. As if I care about this right now. But B prime is very similar to B, and B is a basis. We're taking out one particular index. So what we have is almost the columns of an identity matrix for B prime, but we've removed column index L. And then we're adding in, so currently as it stands, when you just take out the Lth column, that's not spanning, that's not a basis for the column space of A anymore, because you need one more dimension, because there's only m minus 1 dimensions now that you've taken out one of the m total. So yeah, so you don't have a basis for the column space of A, which is Rm. But once you add in the index k, the point is that you're supposed to once again have a basis, and that's because um, um, basically there's only one entry for this Lth column vector here for which it's non-zero. It's an identity matrix column, remember, so there's one entry for which it's a 1 and it's positive, and that's the rth entry, okay? So let me just go through these lines real quick. So B prime is will be a basis exactly if the columns of AB prime are linearly independent, and that's because, you know, right now we're not spanning all of Rm because we've taken out the Lth column, but once we add in the kth column, if we're spanning, if we're again spanning, then that's by definition a basis. It has to be linearly independent because it's you know, it wasn't spanning before and now it is. Anyways, that's just linear algebra. Okay, and AK. So this is, when will the columns of AB prime be linearly independent? Well, we took out index L, and the rth entry of the column AL is a 1. So for that particular dimension of space, we no longer have a component, we no longer have a vector which has a positive component in that direction. So when we add in the column vector AK, it better be the case that that column vector has a non-zero component in that same rth entry down, and that way we will be able to span that particular direction of space again by having a non-zero component there. So yeah, so this is all true if and only if AK has a non-zero entry in the same position that AL did, and even if there's other entries of AK that are non-zero as well, it's okay because the rest is the identity matrix. The fact that we're so close to being a complete identity matrix will you can verify for yourself if you want that will give us a basis, as long as this the corresponding entry in the kth column vector A of A is positive for the same entry as it was for AL. So here's a picture to just help visualize all that. So the matrix A consists of all these columns, A1 all the way up to AN, and here's the two specific columns we care about. I don't know what order they come in, I just had to draw it some way. So AK and AL, and we're looking at the rth row here. I'm saying that in the rth row of this matrix, so in the rth entry down of AK and of AL, these are both positive. Now, why is that true? Okay, so because L is the Lth component of the overall set of indices 1 to n, but amongst the basic indices, it was the rth one, and it was part of the identity matrix. And so that means that, so again, if I'm counting amongst the basic indices, where here the basis I'm talking about is B, not B prime, but B. Remember, we counted amongst the green circled, components up above in that prior picture. Well, we counted R down, and so similarly I can count R across here, and that will land me at A sub L here, amongst the basic components. And so yeah, this is identity matrix, and so it's R entries of the identity matrix down, and so that must mean that the rth entry in this column of the identity matrix is the 1 entry, and the rest are zeros. So yeah, so when you're thinking of all these columns, you should be thinking that for the basic ones, the basic ones corresponding to basis B, they're the identity matrix columns, and they correspond to wherever these basic indices are occurring. And if you took out all the rest of the columns and you just smashed those together, you get the identity matrix. And so this is the rth one there, and so that must mean that the rth entry down is the 1, which is positive. And then on the other hand, for this entry, why is this entry in the rth entry down in this column positive? So let's just keep going here. So ARL equals 1 because it's part of that identity matrix. It's positive, and so I don't explain. So, okay, so ARK, just by definition, basically, ARK is positive by choice of what R was. Remember, we picked R to be some index that realized that minimum ratio of the BIs over the AIKs, where the AIKs were positive, and and so and so that must mean in particular this one ARK is positive, and so that must mean that both these entries are positive here, and that suffices to show that when you take out this column from your basis B, but you add in this column to make a basis B prime, that you will still span all of Rm, and in other words, B prime really is a basis. So yeah, so that's the conclusion here. So AB prime, the columns of that really does form a basis for the column space of A, so it's a basis. So those address those last two facts. So here's just the algorithm itself. So we're not, by the way, I mean, I'm going to just show the algorithm itself, but we're not quite done there. There's analysis of the algorithm as well, which I'll just say something brief about. So I mean, the simplex algorithm, this is just for fun, really, just having this here. So you can just see compactly what the computerized, pseudocode kind of version of it would look like. Input is a linear program, P of this form. So I named the linear program parentheses P, just so I don't have to keep saying linear program. Then we have a feasible basis B. And by feasible basis, what I mean is just that there's a corresponding basic solution to B, and I'm saying that corresponding basic solution is feasible. That's what it means to be a feasible basis. It's equivalent to having the basic feasible solution, because if you have a feasible basis, now just take the basic solution, which we know how to do, and that's the basic feasible solution. So anyways, okay, so that's our input, and the output is either an optimal solution or data proving that the linear program. I said here that it's infeasible. What I should really be saying is data proving that it's unbounded. We actually, if we're starting, so this is just actually fundamentally the wrong word to be using here. Not infeasible. Infeasible means that there's no solutions at all. But you should recognize why that's actually the wrong word to use here, because we do know that there's a solution to our linear program, because we started by assumption with a solution. In fact, it was a basic feasible solution to this linear program. So there's no way that there's no solutions. There's at least one. We started with one. So I don't mean infeasible here. That was a mistake. I mean unbounded. So either the output is an optimal solution to P, or data proving that it's unbounded. So yeah, so just cross that part out there. Okay. Anyways, that's the output. So how do you get that output? Well, what you do, you write P in canonical form for this basis B, and let x bar be the corresponding basic feasible solution. And that's because we have a feasible basis B. So if we're in that first corner case where all the CNs are less than or equal to 0, we can stop and conclude that x bar is optimal for reasons that we addressed above. But on the other hand, if that's not the case that we're in, then there's some k index, non-basic index k, such that the associated C component is positive. And now, if we jump to the other corner case, if for that particular index k, if AK, the column vector, is less than or equal to 0, then we can again stop the algorithm and conclude that the linear program is unbounded, again for the reasons that we addressed above. But assuming that corner case isn't true either, now we know that this the ratio of these BIs over AIKs, for which the AIKs is positive, exists, and so this is all well defined. So let R be a particular row index where this minimum is attained, and so that row index is R, and then I'm counting again. This is the rth basic index, but amongst all the indices, it's the lth one. And so that lth index is what I'm concerned with. And so what I do is I make a new basis by exchanging the indices k and l. So k jumps into the basis, l drops out of the basis, and that gives me a new basis here. And as we've shown, that there is a basic feasible solution associated to this basis, and that's exactly the x prime that we constructed throughout this video. So, but anyways, now again, so that must mean we have a feasible basis b here, and so we loop to the beginning where we start by saying, well, what do we start with? A linear program, which is has a feasible basis b, and we know that this new basis upon exchanging is again feasible. So then you just go right on through again, and at some point you will land in one of these corner cases, basically, and then once you land in one of these corner cases, it'll terminate, and that's how it works. But there's one thing which, again, maybe your spidey senses are going off. I said at some point you will land in one of those corner cases. I haven't proven that you will, and it's actually a bit tricky. So first of all, so here's what if you're just trying to make something go wrong, just to see if it's possible for something to go wrong, what would you think? Well, what if t equals 0 at some iteration? So here's just the things that are possible. I'm not gonna give explicit examples of how this all works, but here's just things that are possible. It could be the case that at some iteration t equals 0. That is to say that we wanted to boost t as much as we could, but that value actually we couldn't boost it at all. It started off at 0, and then we could boost no further actually, because there is a constraint that forced t to have an upper bound of 0. And of course, then you can't increase t anything beyond 0. So you're stuck at 0. So t is 0 for this iteration. And what happens in that case is that you'll get a new basis once you go through the iteration upon doing the exchange and all that. But you're going to end up with the same basic solution. So remember, each basis has a unique basic feasible solution. So if I start with a basis, I can get a single basic feasible solution that's well defined. But it's not the other way around. If I have I can have different bases with the same basic feasible solution. Okay, so that is totally plausible. And so what that means then is that, okay, I started with a basis and I had a basic feasible solution, and then I do the iteration where t is 0, and I get a new basis with the same basic feasible solution. I haven't actually changed the vector that I'm at. It's possible then later, imagine that on the next iteration, actually, you when it comes time to maybe at the next iteration t is 0 again, and when it comes time to figure out what exactly the exchange of the indices is, maybe we exchange right back to where we started. That is, we did one exchange, we exchanged k and l, but now we exchange right back. So l jumps back into the original basis again, and k, back out again. And so we're at the initial basis that we started with. And not only are we at the initial basis, we will again have the same basic solution. And in that case, that would, now you're at the same exact point that you were at the beginning of the algorithm. That would just correspond to an infinite loop in this algorithm, because it would keep doing the same thing over and over in this loop that it can't get out of, because it's exchanging basic elements back and forth. And then more in general, it's just possible to cycle. You don't have to do an exchange and then directly exchange back. It's just possible that you keep generating new bases, but with the same basic solution. Or in fact, you can jump around basic solutions as long as the objective value doesn't increase, which is not the case when t equals 0. So, but anyways, the point is just that at some point you'll come back to the same basis that you started with the same basic solution. And I know I'm describing this in completely vague terms, but it is entirely possible that all of that happens. You can construct examples where that would happen. And so, yeah, the algorithm would be stuck in an infinite loop. So how do you fix all this? So this is all very bad. You'll never jump into one of those corner cases. What we want is at some point for this to end up in a corner case that we discussed and terminate. But currently we don't know how to fix that. But here's the fix. Here's what you do. You adopt a convention, which is called Bland's rule. And the convention is when there's a choice between multiple indices, you always choose the smallest index. So that, like, for instance, we said that what is k? The index k is, well, it's just any particular index that you like amongst all the indices for where the corresponding c component is positive, right? That's what k was. Well, there's probably multiple components for where c is positive. So what we're saying is the convention would be to take the smallest of those indices. So if C2, C4, and C5 are the positive valued components, then take C2. That's the one you would take, because 2 is the smallest index. So, and then similarly, where we had a choice for the R index as well, right? There could be, where we realize that minimum ratio, there could be multiple realizations of that. So, but again, you would take the smallest index there. And what happens is that simplex algorithm, when you've adopted this Bland's rule convention, it is guaranteed to have finite termination. There's no infinite loop. So we will end up in one of those corner cases at some point. So I'm not going to prove that. It's actually kind of a non-trivial fact. It's very ezy to say. You understand what I've just said, but it's very technical to prove. Actually, where I get this information from Gwen and Kuhneman and Tunsil, Gentle Introduction to Optimization, and in that book, in section 2.5, I think exercise 10, I think, they go through an exercise that would breaks it up into multiple parts about how you would actually prove that using this Bland's rule actually guarantees finite termination. So I guess, technically for completion, it'd be nice to include that. But I would definitely, at the very least, need a separate video. But I'm probably just going to gloss over that for now, just because it's a very simple thing to say, and the big idea of what the simplex algorithm is exists independent of that convention. So it's a very technical thing that you can get lost in the weeds doing. But I mean, of course, if you want to complete everything, you should do it. Okay. But anyway, so I'm not going to say anything more about that. We're just adopting that rule, and we're taking for granted that it has finite termination. So the final question to ask then is, how do you find this initial feasible basis? Or equivalently, how do you find the initial basic feasible solution? Because presumably you just start with a linear program, and you don't know anything about any basic feasible solutions. All you have is a linear program. But on the other hand, you need that basic feasible solution in order to catalyze this entire process so that the algorithm can iterate over and over. It needs to start with a basic feasible solution. So how do you generate that initial one? And this is what's called, you introduce something called the phase one problem. And so phase one just gives you the data that you need. So phase one finds a basic feasible solution from scratch. So all you're given is the linear program, and you run phase one, and that'll give you a basic feasible solution. And now you feed that data into this algorithm that we've just discussed, which would be phase two. And so we use that basic feasible solution at that point and follow the simplex procedure that we just outlined. So like technically overall, the simplex algorithm would be both phases. But really this is the phase two would be like the main phase. Phase one is like a preliminary phase, is how you would think about that. So yeah, anyways, how does this phase one work? Well, that's going to be for another video. So this one's certainly gone on long enough, and so it requires its own video to address that. So if you take for granted that we can get a basic feasible solution, we're done. But to complete everything, we need to show how to generate the basic feasible solution, and it's actually pretty creative the way that it works. So in fact, well, I'll address it there, but we're going in the correct order, basically. It's good that we started with this process, and and then we'll discuss how to solve the initial process. Counterintuitive as that may seem, it may seem like you want to figure out things in order, but in fact, it's better that we're doing it out of order, in the sense we did phase 2 first, and then we'll talk about phase 1. You'll see why that'll make more sense when we actually talk about phase 1. But anyways, that's it for this video. Thanks for watching, and